In 1874, Georg Cantor, a German mathematician, published a paper that launched a new branch of mathematics called set theory. A set is just a well-defined collection of things. So the two shoes on your feet are a set, as are all the planetariums in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like a third, 5 halves, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal. He wondered, are there more natural numbers? Or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up one-to-one with an integer. If we can do that with none left over, well then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assume we've done that. We have a complete infinite list with each integer acting like an index number, a unique identifier for each real number on the list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the first digit of the first number and adding 1. Then take the second digit of the second number and again add 1. Take the third digit of the third number, add 1, and keep doing this all the way down the list. If the digit is a 9, just roll it back to an 8. And by the end of this process, you'll have a real number between 0 and 1. But here's the thing. This number won't appear anywhere on our list. It's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on down the line. It has to be different from every number on the list by at least one digit, the number on the diagonal. That's why this is called Cantor's diagonalization proof. It shows there must be more real numbers between 0 and 1 than there are natural numbers extending out to infinity. So not all infinities are the same size. Cantor called these countable and uncountable infinities respectively, and in fact there are many more uncountable infinities which are even larger.